School.
Live from the Key TV studio to your TV and on the web, it's Homework Hotline. Go to homeworkhotline.tv to ask your math or science questions.
Hi, welcome to Homework Hotline. My name's Dan Scofield. I teach science at St. Bernard's Academy.
Hi, my name is Amy Taylor, and I teach 8th grade math at Sunny Brae Middle School in Arcata.
So great to have you here, watching us, streaming us in. You can go to the link, homeworkhotline.tv. From there you can go to a YouTube video and click on that, and that's where the live stream is. And you can ask your science or math questions while you're there, and we will try our very, very best to answer them. Homework questions or just questions you had about math and science you're wondering about?
Yeah, I tell my kids, if you generic, like what's a slope, or they can just be like, read the problem right off their homework. So either way works, and same with science.
Right, I know I have some students that are studying for tests, so you can ask test questions and we'll try our best to try to get them
maybe
answered.
like some of the schools do final, or around this time of year, finals.
Yes, we are doing that.
Okay.
So while we're waiting for questions, I do have some science things. We were studying, in one of my physics classes, we're studying circular motion. And I thought I would bring in a few things that we were doing in class and some of the things that we weren't doing in class. I got this thing at a craft store. It's a holiday wreath starter. And I know I'm going to use it for some of my kids will be making holiday wreaths. And I thought it's actually a little rough compared to the hula hoop doing it, but I thought this would be kind of fun and festive to do. Festive to do to show this. So something spinning in a circle needs to, if I spin something inside something like this, it goes in a circle because it's being pushed towards the center. And so it has to have something pushing it towards the center or pulling it towards the center in order for it to spin in a circle. And that force that pushes it towards the center is called centripetal force. And so in this case, it's just the wreath. I guess it's straw in there or something like that. And it's just all bundled up, and it's causing you to be able to push it towards the center, and that way it goes into a circle. And a fun kind of game that I maybe could play with Amy here is to say where I've got the man standing over here, right off to the side. We can put him pretty close. Stand up the man, and then let's maybe put him like a little bit.
Like this?
Or like right there.
Far away.
There you go. So that makes it a little bit. So the question is, like, where should I lift up the wreath in order for the ball to hit the man? And then I guess the question is, should I do it like when it's right there?
Probably not.
Or right like next to it so it goes straight off? The question you should ask yourself
here.
is which way, if there's nothing forcing the ball into the center, which way will it tend to go if all the forces are let go? Like one of my students asked, Mr. Scofield, what would happen if all of a sudden the sun disappeared? What would the Earth do? And I said, well, it would be bad for us, but it would go flying off. In what direction would it go? But so the question, and I'm going to have Amy say lift, and we'll just, right when she says lift, we're going to lift it. But we're not going to be kind of quick here.
Oh, geez.
Okay, let it go around once, and then
say.
Whoops, I got to go harder.
Lift.
Yep. That was my bad pulling up on the wreath.
Lift.
Ooh, really close. I guess the point is here that it's once you remove the force that's pushing it in, it's going to go, we just say it just goes tangent to the circle. Tangent to the circle. So yeah, and I know she was trying to do it, that's my poor lifting, but it was right about here. And then if I lift this up, it goes tangent off. Let's try it one more time. Get ready.
Now.
There we go, we got it, okay. Anyway, so it goes tangent to the circle, and it'll take out the person.
And tangent just means it like
Yeah.
you touches at one spot.
Touches it
Yeah,
once.
I don't know because some young
Makes a
kids
line.
might not know.
Right, no, and that's because there's no force pushing it any other direction,
Yeah.
and then according to Newton, if no force is pushing it any way or pulling it any way, it continues to go the direction it was going. But in any particular case, at any particular time, it's going to go in the direction tangent to the circle. At any given point around the circle, it's going that way. So that's what's happening to it. What is phosphorylation? What's phosphorylation? Do you mean? I guess it's person who's asking this question. This is having to do with photophosphorylation. Photophosphorylation means that phosphorylation in the presence of light, and phosphorylation means that it usually has to do with adding phosphate groups to an ATP. It's adding phosphate groups to an ATP, going from ADP to ATP. And this, we talk about photophosphorylation in photosynthesis, and this is happening in the chloroplast. And what happens is the light energy hits the chlorophyll and excites the electrons in it, sending it up to a higher electron state. And as it goes down, it uses that energy to pump hydrogen ions into a part of the chloroplast, and then it uses that to generate ATP. I mean, it's the kind of the short answer to that. But yes, it happens in light energy. As those excited electrons go to a lower energy state, it uses that loss of energy to go and eventually create ATP. That's what photophosphorylation is. All right. It's Kai.
Yeah, and they have homework questions about this, and then he's saying, what does bivariate categorical data tell you about population? Typically, bivariate is like 2 and 2 things together. If there's any type of specific question, I know it's in your homework, then maybe type that in, because I generically can help you, but I can help you with your homework too, because I know he has homework problems on that right now. And then we'll go to the next question, but if not, I'll just do a generic thing.
Okay.
Okay.
Okay. I'll answer the other. We can talk about the next question real quickly. Caitlin is asking us, if the Earth was flat, would gravity have a different force? I'm guessing
Yes,
force.
Yeah.
The force of gravity is dependent upon the mass of the object and then kind of how far away from it you are from the center. So if the Earth was flat, and it had the same mass it has right now, it'd be a problem, because all that mass would be trying to go to the center. It would be naturally trying to form a sphere, because everything tries to form a sphere. It's like, that's why when you have water droplets, if you just let them go, they don't form squares. They don't form pancakes. They form spheres. And so there's so much mass in the Earth that it would just all of it be forcing it towards the center. So if the Earth was flat first of all, and it had the same mass as it does, it would probably break in a bunch of pieces and form a big molten ball, is what it would do. And all that energy would pull it together. And so it would be and also the gravity would be different. Let's say that didn't happen. It's the amount of mass that's between you and the center of the Earth would be different in different places, right? If you're on like the middle of the record player, on the record, you would have, I don't think there would be that much mass, but anyway, so yeah, it'd be very different. It'd be very different. It would be really, really weird if we were on a pancake.
Yeah, well, like you said, it would want to spread it, so it would spread out and eventually become a sphere again, or something.
Yeah, it would naturally things form spheres. All mass forms spheres if you just let them go. You just blow a bubble. What does it make? It's pushing itself inward all the time. And so it would be different. It would have different gravity forces depending on where you were on that sphere, on the flat pancake. But
yeah, and so the bivariate data, when they start studying this, it's basically 2 by 2. So you're taking 2 things based on the other 2 things, and it reminds me of like a Punnett square. I know they do in science, genetics, and you're just like what they're having them do is they're giving them like a percentage or something, and then it's a 2 by 2. It's almost like a multiplication table, and I'm not sure exactly what he's dealing with that, but you could just look at different things on population dependent on other things on population. I don't know if they want to do like how big the city would be. I don't know. Some things end up doing things if there's like a virus, that's I mean, there's just different things. So I'm kind of like, that's generic. Oh wait, did he?
Yeah, he said he's giving us a definition of categorical data, and that's.
But which category?
Right.
It just
that's
depends. Yeah, it's more generic.
Yeah, it's
but I can definitely help you. Well, I mean, like I said, I would just make a table. What are the conditions? If there's 2 and then there's 2 conditions here, that's going to be 4 different 2 by 2. That'll make 4 spots. It's almost like a multiplication table. They're just starting it. And so I don't mind looking at it tomorrow, but I'm not exactly sure what you're asking. And I'm sorry.
If you have Kai, if you have a particular question you're trying to answer, I think that might be focus question in general.
Okay.
Well.
Yeah, I would just say, just pick something in population that's dependent on something else in population. I just said like size of city population, maybe rural, maybe doing rural to city. You could do anything like, we had ones where it was like, if sounds bad, a virus or a bacteria affects the population. I don't know, you have to think of, I guess you can just think of anything that affects the population and then think of how that would affect the other part of the population. If that's happening, I don't know. Yeah, I don't know exactly. But
is it a function that, like one category's affecting that?
Yeah. So I don't. Yeah.
Okay.
All right, but I'll definitely help you tomorrow then.
All right. Thanks.
Thank you.
Thanks for the questions, everyone. What else can we talk about circular motion? This is kind of fun. We can do a little math with this if you want. All right. So this, and I will try not to hit you in the head with this, but this is a fun thing you can do with math. It has a little bit of math with it. And so I've got a couple parts to this. One is I have a hanging mass that weighs 200 grams, and I have a spinning mass that has a mass of 20 grams. And so when I spin it around, I'm trying to get this in equilibrium. I'm going to have it this far out because that means there's an 80 centimeter radius here. All right. And so the question is, how fast do I have to spin this thing?
That's 20 grams?
That's 20 grams. How fast do I have to spin this thing in order to hold up my 200 gram mass? All right. And so again, to get this to spin, I have to have a force going inward. That's a centripetal force, and that's being provided by this 200 gram mass. And so we can figure out how much force that is if you want. I mean, it's all you have to do is to figure out the force is just mass times gravity, according to Newton's second law. Mass times gravity is force. And so from gravity, so it's 200 grams, which is 0.2 kilograms, so 0.2 times 9.8. I don't know if you want. Let's write this down. So we can. So it's going to be 0.2 kilograms times 9.8 meters per second squared, and that's the gravitational acceleration on the Earth, which we are. That's where we are. And so we got 1.96. Is that 1.9?
Yeah, you said 2 tens times 9 and 8 tens.
1.96 newtons of force. And the way we figure out the force that's going to be provided by this is it will be the acceleration times its mass. Will provide that force. So it's the acceleration times its mass, which is going to be, so we can figure out what the acceleration should be because we know its mass. So it's what is 0.02. 0.02 is its mass, 0.02 kilograms times whatever its acceleration is. So we just need to go divide that back in again. We'd have to say. So
you're saying you want 2 into
that. So its mass times acceleration is going to have to be equal to 1.96.
Yes, and the mass is this.
0.02. So its acceleration would have to be.
Yeah, we do the. You do the inverse. So for math.
Yeah, we do the inverse.
And the inverse. So we have the acceleration times 200ths. I would just
go back
multiply. Oh yeah. Well, this is 100. Yeah, just off a decimal place. But if you did this.
Yeah.
Times by 100, so then you have just 96 divided by 2, right? Is that what you're saying?
Which should be what 98.
But it's going to be 98, right? Not 9 and 8 tenths because you're doing 200.
Yeah, and be 98 meters per second squared.
Yes.
And so, and then so the other thing we can do with this is say, the other thing we can do with this is to say, that 98 equals the acceleration, and we figure out the acceleration by going it's v squared over the radius. So 98 equals v squared over the radius, which is
radius?
0.8 meters, and so then we can figure out
The radius is 0.8 meters?
Yeah, 0.8 meters.
Is that what you said?
Yes.
Okay.
And so
Then we can multiply, do the inverse of divide, which is multiply both sides by 8. You said 8/10, right?
8/10 is
Yes.
80 centimeters, yeah.
So 98 times 8, we got the 64.
All
And then
this
we got 72, 78, right? So 78 and 4/10, and then we'd have to square root that. So
which
the
is
inverse
around,
of squared is square
real fast. Square root about
Well, square root of 81's 9.
9. So it's going to be we can
A
just say
little
it's
less than 9.
little less
8
than
and 9
9.
tenths. 8 and 8
9.
tenths.
Okay.
We'll say 9.
So it has to go 9 meters per
It's
second.
about 9. And we say, well, I tell the kids when you square root, you get a positive or negative, but this would be
Right.
positive.
Right. In physics, it's less likely to have a negative number. So that is meter. Well, you could be going backwards, I suppose. It's about 9 meters per second, and so
Meters per second.
and then so what we can do is to figure out how fast it's going. It's going to make a circle, right?
Yes.
And so we can figure out how fast it's going based on
Yeah.
how what is the velocity of this thing. So we're going to figure out it's going to be about 9 meters per second. So let's measure. We can try to measure how fast it's going to go.
Okay.
All right.
How do we do that?
So we're going to time it.
Okay.
So I'm going to have you time.
Okay.
Just tell me when to start, and then I'll start counting revolutions after I get it going without hitting you in the head. And it's not hit you in the head. And then you just tell me to start, and maybe count 10 revolutions. We'll divide by 10.
Okay.
And then, but let me get it in equilibrium first. It's got to get way out here. So the radius is going to be about right here. So just
Okay.
to kind of keep that in mind.
Okay.
So I don't hit you. So that would be bad. Okay. And then so do you see if I spin it faster, it goes up.
Oh, yeah.
And if I spin it a little bit slower, it goes down. But I want to keep it right about here because that's where but then there's this problem of the mass starting to swing around. Okay. So
Okay. Hit
I think
start.
I'm ready. Anytime
Okay.
you want to tell me to start.
Okay, start.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how long did that take?
5.68.
5.68. Okay. So 5.7
Okay.
seconds for 10 revolutions is how much time for one revolution?
So what you said is 9 meters per second.
Well, let's
Okay.
yeah,
What are you asking? Sorry.
No.
Okay.
It is 9. Right. We need to go about 9 meters a second, but we got to
Okay.
figure out what that is. How fast is it going? You said 5.7
Let's say 5 and 7/10.
for 10 revolutions.
Yes.
So one revolution would be about
Yeah, I like a half.
0.57.
4.6.
0.56 seconds per revolution, right?
Okay.
So how
It's
that
about,
was
we
a
can say about a
time,
half, a little over a half.
a little over half, and how far did it go?
So it went around, so you said it went around,
One circle, right?
yeah.
So that's 2 pi r.
Okay.
So we're going to have to use 2 pi r divided by 0.57.
So 6 and 2800ths divided by like 0.6, like 12 or 13?
Yeah, but, I mean that's 2
0.6.
pi. Let's see, 2 pi r. It's and the
2
radius is
pi r.
0.8.
Oh, 0.8. Sorry, I didn't do that. So 2 pi is 6.28 times
0.8.
0.8. So that's 6 times 8 is 40, like 50, like 5.
About 5. Okay.
Yeah.
So 5 divided by the time, which is
A half. So
Half.
10
yeah,
ish.
10-ish. So it was
Yeah.
going. It was going
or
about
a little bit less because it's 0.57. So a little bit less.
0.57. So
Little bit
it is
less.
going. It is. This is where theoretically it should be going 9 meters a second.
We're ballparking.
in
so I would say it's
experimentally, it was going about
yeah, no,
10.
Yeah,
About
or a
10,
little
less
than
than 10.
Yeah.
So I mean, we're at least in the ballpark, right?
That's great. That's
Isn't that cool?
exciting.
It's like I mean,
Proving math science.
Physics is just taking all these math problems that we do in the math class, and we get to play around with toys and figure out if it actually works, which is pretty cool. All right. So what else can we do with this stuff? We can again, centripetal force is a thing that you have to pull something in to get it to go into a circle. We see some parlor tricks sometimes about this won't be uniform circular motion, but we can talk about the centripetal force that keeps the something in the bucket, right? So I can pour some water in the bucket. I mean, this is the last week of the season for Homework Hotline, so I'm going to try not to get you wet. Maybe I'll come out front with this. I'll go over here, and just so I wreck the cameras instead of the guest spot. All right, so I'm going to go step out here. Here I go. All right, so I'm going to go this way. Ready? Okay, so there's water in this bucket.
Okay,
right?
yes.
Okay, so there's water in this bucket. The rope is tied pretty good. So the thing is, why, if I spin it around, why isn't the water coming out of the bucket? I'll do it one more time, just to risk things. I can even go slow like that. You can kind of feel it sloshing.
Oh, jeez, I heard it.
It's hard not to get it to slosh a little bit when it does that. But this isn't really uniform circular motion. Uniform circular motion means it's going constant speed around and around and around. It's going faster coming down than it is at the top. But still, why doesn't the water come out at the top? And it's not because there's a force that's pushing it outwards, right? It's because it's going outwards already, but it's pushing against. Its inertia is pushing it against the sides of the bucket. Now, if I stopped it up there at the top, then I think I would get wet. But it's continually trying. It's trying. The water is continually going in the direction it was going before, and which is pushing against.
Which is the same thing you're doing here.
Exactly. It's the same thing we're doing here. It's the same reason why this ball doesn't all of a sudden go towards the middle.
Yeah.
It's the reason it's pushing up against the side of the bucket. And so you can keep doing it. I could do it with a smaller thing as well. Another thing that's kind of fun to do, there are these toys. Let's see if I can get this to work. There are these. Yeah, these are fun. And this is when pigs fly. It's the joke that goes with this. And so this is called, it should sweep out what's called a conical pendulum. And then you could have this thing hanging on. No, hold on. You got to get this start facing the right way. Let's see, of course it's not going to. Come on. Awesome. I think the thing is spinning the other direction, so come on. You can do it. You can do it, Piggy. There we go.
Doesn't want to face the right direction.
Doesn't want to face the right direction. There we go. Okay. Here we go. So you can get a ball or anything like that,
cool.
just to hold it and kind of give it a little push from your hand to get it to go and do this. But this is I'm just holding this. I'm not moving it with my hand at all. And it's sweeping out. It's sweeping out a motion. And so it's doing this. I know it's doing this. And you set this up on your ceiling and have just hours of fun watching this thing. Eventually, it's going to get wound up here, and it's not going to be able to stay there. That's why usually they're spinning on a little device. But it's going here. It's able to propel itself, and it's able to propel itself in that direction. And now, if there was no air in here, I could just get it to go like that, and it would go pretty much forever, right?
Yeah.
It's the same reason why you can put a satellite into orbit, and it stays up there because it's going fast enough that it's continually falling to the Earth, but it keeps missing the Earth. And so this thing needs to have some force pushing back against to resist the air resistance, because the air resistance is keeping it would eventually have it slow down and stop. If there was, if I do this and I just let it go, if it doesn't push anything, it just eventually slows down and stops.
Yeah.
Because it has some force thrust back behind it, it can push along, and it gives it some velocity, so it goes into that cone. But if you think about the forces acting on the pig, there's a gravitational force pulling down, there's a tension force from the string, and then there's a force pushing behind it from the wings, and the force pushing the other way against it from the air resistance. So all these things, sweeping up. Cool. You figure out all kinds of things. You want to do some more math with that. Figure out, how much tension is on the string. You figure out, how fast it needs to go. How fast is it going? Yes. Using those same formulas that we just used. So here we go.
I think there's just some.
Okay. Right. Do you want to read the joke? Because I know the answer.
Oh, you do?
Yeah, why was the math book sad?
I don't know.
Because it had so many problems.
Oh, that's funny.
We know them all, Caitlin. We've heard them all. All right.
That's funny.
So.
I like those puns.
I do. I love those puns. All right. So here's another thing that has to do with. Well, let's do this. And let's do a little more. Let's see if I can make the studio wet. Yeah, we've got just very little time here. So for the last little bit, I'm going to make sure, let's see, I'm going to put this cup of water on this platform.
Okay.
And can I spin this platform around and not get everything wet? So I'm like all this technology, cameras, everything like that. Amy's nice shirt. Let's see if I can do it. Whoa. So same reason. Again, it's not flying
full of
away.
water. Oh my God.
Oh, I might do it again. How about twice around?
Okay.
Take my chances here. Ready? 1, 2. Up. Nope, I'm not going to do it. All right. So didn't get you. There you go.
No
oh,
water.
Are you glad
dry.
you subbed today?
I'm dry. Better when you
So
go
again, why doesn't this fall off the platform? Why doesn't it? Because it's continuing to go in the direction it was going. There's a little bit of
trust
friction.
science there right now.
You got to trust science. Hey, we've got to trust science all the time.
Exactly.
Right.
But you know what I mean? The first time you do it,
Right.
when you've never done it before,
Right,
you're like, I know
exactly.
it should work, but.
I always like to do it right in front of the students that need to be paid attention to the most. Right in front of them. That's always the best. So that's circular motion, and we'll be back again on Thursday.
Thank you for tuning in.
To do some more fun science stuff, and I'm glad you guys tuned in.
Bye.
See you around.